In this lecture, we'll get even more practice with proofs by induction by exploring actually one of my favorite number sequences, which are the Fibonacci numbers. So the Fibonacci numbers, well, they're defined in the following way. So they're defined as follows. Let's start with f of 0 actually. So f of 0 is 0, and then f of 1 is 1. And then after that, to get the nth Fibonacci number, you add the previous two. So f of n is f of n minus 1 plus f of n minus 2. And this last one is valid for n larger than 1. Okay. So what does the sequence look like? Well, it starts out 0, and then 1, and then you add the previous two to get a next one. So 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, then we have 8, then we have 13, 21, 34, 21 plus 34 is 55. So it's adding the previous two to get the next one. You can go on however long you want. Next one should be 377. Let's do one more, maybe 610, etc. So this is the sequence of Fibonacci numbers. And so these are pretty easy to define, but they hold all kinds of rather interesting properties and patterns. Some of them are easier to spot. Some of them are pretty deep, actually. So yeah, let's just so this is F1. Some people like to start with F1 and F2 instead of F0 and F1. So it depends where you want to start. That's F3, F4, F5 is 5, F6 is 8, etc. And so the first thing you might explore is there's one kind of pattern you might try to explore is what happens if you take sums of Fibonacci numbers. So for example, F1 is just 1, F1 plus F2 is 1 plus 1 is 2, F1 plus F2 plus F3, and I can do F1 plus F2, etc. You get the idea. F1 plus F2 plus F3 is 4, 1 plus 1 plus 2. This one is 7. And the next one, I won't write it all out. F1 all the way up to F5 is, F1, F4 is 7, plus 5 is 12. And I'm not sure if you notice a pattern there. I don't notice anything obvious, but now when I look back at this sequence, I notice a few things. So, yeah, so this 7 looks like it's 1 less than 8, and the 12 is 1 less than 13. So maybe that's the pattern there. Maybe the sum of, in fact, yeah, let's guess. So maybe the sum of F1 all the way up to Fn is it would be 1 less than whatever this Fibonacci number is. So what Fibonacci number is it exactly? Well, if this is F4, it looks like the sum is 1 less than F6. So it looks like you have to go up by 2. So f of n plus 2 minus 1. So that's our guess for the formula. So sum of a bunch of Fibonacci numbers just happens to be another Fibonacci number. Well, almost. Okay, so this formula seems to be valid for any n bigger or equal to 1. Let's try to prove it. So this would be a good one to try on your own. And then when you're ready to keep watching, you can unpause the video. But yeah, we start with the base case. It's going to be an inductive proof. So what is the sum of the first Fibonacci number? Well, it's 1, right? Does that equal F3 minus 1? That's what the formula tells me. What is F3 minus 1? It's 2 minus 1. That checks out. So that's our base case. And then our inductive step is suppose the formula holds for some k. You might notice as I go further and further, I might leave out a lot of the writing that I put in before. It's typically in math papers when you do an inductive proof. You won't spell everything out, but you'll give the reader enough to sort of follow the logic. So I'm now in my inductive step, and what are we going to do? We are going to look at when we have the sum up to fk, and then fk plus 1. And we're going to try to show that that's equal to, I guess this side would be f of k plus 3 minus 1. But we're not assuming that. We are assuming the formula holds for k, though, which means this part there actually just equals f of k plus 2 minus 1. But we still have this f of k plus 1 here. And what can we do now? Looks like we're kind of stuck until we remember the definition of Fibonacci numbers. Right? F of n is f of n minus 1 plus f of n minus 2. And see, I see f of k plus 1, f of k plus 2. The sum of those two equals f of k plus 3. Okay. And the sum of the two previous numbers equals the next one. So, and this is exactly what we wanted to prove, so we're done. So that's one example of how induction can be used. Let's look at a totally different kind of property. So this will be divisibility. I don't want to give you the idea that everything's just about sums when we're dealing with induction. This is an extremely interesting topic when it comes to Fibonacci numbers. There's some really deep patterns involving divisibility, but there are also some that are easier to spot. And I think the one that's easiest to spot, at least for me, probably the first one I spotted was, notice F5 is 5. And then if I consider all the Fibonacci numbers that are divisible by 5, the next one is this one. Well, that's F10. And then this one is F15. And I guess even 0 is divisible by 5. 0 is divisible by anything. Which is F0. So it seems like every fifth one, when the index of the Fibonacci number is multiple of 5, it's going to be divisible by 5. So it seems this is one example of a divisibility property. And the 5 is a bit special because, for example, every seventh one is not divisible by 7. This doesn't work for every number. 5 is a bit special, actually. So it seems every fifth Fibonacci number is divisible by 5. How can we write this a little more clearly in every fifth Fibonacci number? I guess we could say f of n when n is multiple of 5. A clearer way to say it is like f of 5n. That really forces the index to be a multiple of 5. So we can say this is divisible by 5 for any n. I'm saying every fifth number is divisible by 5. By 5 for all natural numbers n. Okay, let's try to prove it. This one's a bit harder. So but the base case isn't hard. So you can pick n equals 1 for your base case. You can pick n equals 0 even, right? Because f0 is just 0, and that's divisible by 5. In fact, it's divisible by any natural number you want. It is divisible by 5. Okay. So next we'll suppose, that's our base case. We'll suppose, before we even do that, I've got an issue here, which is this seems rather difficult to use induction here, because unless it was some kind of strong induction, because how are we going to relate this Fibonacci number, so Fibonacci number like f10, all the way back to f5? I know how to relate that to the two previous ones, right? It's the sum of these two. The challenge is to somehow relate this all the way back to here in order to use induction. So let's first try to figure out how to do that. So first, and then we'll go ahead with our inductive step. So first, let's try to relate just the Fibonacci number to the one 5 before in the index scheme. So we'll try to relate f of n to f of n minus 5. And the way you can do that is, you just use what you know, which is f of n is f of n minus 1 plus f of n minus 2 by definition. And then you can sort of unravel this. So f of n minus 1 is f of n minus 2 plus f of n minus 3. So I'm just applying this formula to n minus 1. So it's n minus 2 plus n minus 3. I still have this f of n minus 2 here. We can group the f of n minus 2 together if we want. And this is a bit tedious, but you can kind of see what I'm trying to go for. I'm trying to get one of these indices to turn to n minus 5. So let's unravel this one next. So f of n minus 2, that's f of n minus 3 plus f of n minus 4. And I've still got this f of n minus 3. In total, I have 3 f of n minus 3 plus 2 f of n minus 4. And let's do this one more time. n minus 4 plus f of n minus 5 plus 2 times f of n minus 4. And what do we have in total here? So we've got 5 times f of n minus 4 plus, I think, 3 times f of n minus 5. So we found that f of n is 5 times f of n minus 4 plus 3 times f of n minus 5. So we've made a link between f of n and f of n minus 5, and this might be very useful. Okay, so we're ready to carry out our inductive step, which is assume for some k, some natural number k. What are we assuming? We're assuming that f of 5k is divisible by 5. We don't even need strong induction here. So I'm just using usual induction. High 5. Then we look at the next one. The next one is f of, so the next value of k would be 5 times k plus 1, which is the same as 5k plus 5, right? So this is the one 5 down in line. So our reduction is only really applying to the Fibonacci number is 5 down the line. Okay, so what now? Let's use our fact that we just proved here. So my n is going to be this. So it's 5 times f of n, 5k plus 5 is 5 times f of n minus 4, which will be 5k plus 1. Subtract 5 off of that. Plus 3 times f of n minus 5, which is just f5k. And now I can use my inductive hypothesis. This is, well, this part here is divisible by 5, multiple of 5, in an obvious way, right? It's 5 times an integer. And then this one here is a multiple of 5 in a less obvious way. It's because it's our inductive hypothesis. But they're both multiples of 5. So this is by our inductive hypothesis. Okay, and that means, yeah, the answer is going to be a multiple of 5. It's whatever I get. Not sure what it is, but, well, it's this, right? But it's a multiple of 5 because it's a sum of 2 multiples of 5. And that's the proof. And there are many other interesting divisibility properties you can prove using induction. Let's look at one other interesting aspect of the Fibonacci numbers, which has to do with their rate of growth. What do I mean by rate of growth? So a sequence has a rate of growth. It can be something like linear. Does it get bigger by a fixed value approximately, or quadratic, or cubic, or exponential is another common one, etc. And so you might wonder, what's the rate of growth of the Fibonacci numbers? And the following problem will prove actually that it's at least exponential. So let's prove that. This will be a good one. So prove that f of n is greater or equal to 3 halves. Don't ask me how I got that number, but 3 halves, 1.5 to the n minus 2, which is the exponential function in n. Okay, so, and this holds for n greater or equal to 2. Okay, so it's at least an exponential growth rate with the exponential 1.5. So the base case is going to be f of 2, as we're saying for n greater or equal to 2. What is f of 2? It's 1, right? F of 2 is 1, which is, well, okay, and then what do we have on this side? We have 3 halves to the 2 minus 2. 3 halves to the 0, which is also 1, but 1 happens to be 3 halves to the 0. 1 happens to be greater or equal to 1, so that checks out. If that didn't check out for some reason, you could just modify this to be a larger n. Because growth rate, you really don't care about the first few terms. You just care about what's happening eventually. So you can just modify that statement if you need. And then for our inductive step, we'll let k be. We'll let k be a natural number, and let's assume that. In this case, I think I don't just want to do. I don't just want to assume it for k, but I actually want to assume. Let's use strong induction here. So we're going to assume f of I is greater. The statement is true for every number I between 1 and. Sorry, that should be an n. Obviously, it should be an I. So let's assume this is true for every I between 1 and k, so from 1 up to k. So strong induction. And in fact, we won't need every single one. We're only going to need actually the last two. But nevertheless, what are we going to do now? I should get another piece of paper. Then, and hopefully, so you really have to do a lot of inductive proofs and to see a lot of examples before you really get the hang of it. But hopefully, you're kind of getting the hang of like what even if you're not filling in all the details, you have an idea of what the structure is, right? So it's always a base case. The inductive step, you always assume this for either this K or everything up to K for strong induction, and then you know exactly what I'm going to write next. I'm going to look at the next number. So then what is f of K plus 1? And now is when we have to kind of do some thinking. We want to show you know, at the very end of the day, maybe it's greater or equal to what? I guess 3/2 to the 2 less than the index. So K minus 1. Oh, let's start here though. We're not assuming that. So, and I really can't think of anything better to do than use the definition, right? Okay, now because we wrote this as fk plus fk minus 1, we can imply our inductive hypothesis. So what is this exactly? Well, this is bigger or equal to, fk is bigger or equal to 3/2 to k minus 2. Fk minus 1 is bigger or equal to 3/2 to k minus 3. And so their sum is bigger or equal to the sum of these two, because each of these is individually larger than each of those. Okay. Now what? Well, let's try to simplify this. There's certainly, so for example, if I had like this exponent is 1 larger than that. So if I had something like x to the 7 plus x to the 6, how would I simplify that? I would pull out an x to the 6, that's the largest power I have, and I get an x times x, and I get an x plus 1, right, that's left over. So we can do the same thing here. Yeah, this is larger or equal to, yeah, so we're going to pull out the 3/2 to the k minus 3, and it's going to be multiplied by a 3/2 plus 1, which is 5/2. Okay. Oh, and conveniently, what we want to prove is over here. So otherwise, I would not really know where to go from here. So I'd probably have to write this down anyway. We need to somehow show that this is bigger or equal to this. And so, well, what is this? This is 3/2 to the k minus 3 times an additional 3/2 squared. So is it true that 5/2 is bigger or equal to 3/2 squared? Is 5/2 bigger or equal to, I guess that would be 9/4. Well, that's 2.5. This is 2.25. So yeah, that looks true. So I can claim that this is larger or equal to 9/4, which is 3/2 squared. That was close though, right? But in any case, this is true, and that's equal. I mean, you can even replace it with an equal if you want to this. So we did it. That's the proof. We proved that Fibonacci numbers grow exponentially, at least with this. This is the lower bound for the base of the exponential. And in fact, here's a good thing for you to try. So you try the following. Try to prove. This one's actually a little bit less intimidating than the one we just did. Try to prove that Fn is less than or equal to, right, in this case, 2 to the n minus 2 for n bigger or equal to 2. I think that works. Okay, so see if we can prove that. And so together with what we just proved together, this shows actually that for sure we have exponential growth. So or exponential rate of growth. Yeah, so that is smaller or equal to Fn, which is smaller or equal to 2 to the n minus 2 for n greater or equal to 2. Okay, so it is bounded below and above by an exponential. So Fibonacci numbers grow roughly exponentially. And before I end this, I just want to show you something really neat, which is so what about this 3 halves? Where does 3 halves come from? Well, I didn't have to pick 3 halves. I could have picked something a little bit better. And so it turns out there's a better lower bound. And that better lower bound, we can actually see it in this proof potentially. So it really came down to this step. This was the key step. If this didn't work, then this whole proof wouldn't work, right? If 5 halves wasn't greater or equal to 9/4. So what was the key? Like if I just call our base here x, the base of the exponential, we really needed x plus 1 to be greater than x squared, right? We really needed x plus 1 to be greater than x squared. So we needed, x plus 1 to be greater than x squared. Well, greater or equal. So an interesting thing that you might think about is what if, just kind of coming down here, so what if x plus 1, we chose x, so x plus 1 actually equaled x squared. Well, that must be the best lower bound possible. Like that would make it equal here, and it would still be a true statement, but just barely. And well, this is interesting because this is a quadratic equation, right? X squared minus x minus 1 equals 0. And so we can consider the roots of this quadratic. One is going to be negative, one is going to be positive. But if we take the positive root, and we call that phi, it's going to be about a quadratic formula, 1 plus square root of 1 plus 4 is 5 over 2. And so I could have replaced the 3 halves with that phi. And in fact, this turns out to be exactly the growth rate of the Fibonacci numbers. And it's called the golden ratio. You might have heard that before. And this is a quantity that's intimately connected with the Fibonacci numbers, this golden ratio. In fact, if you take the ratio of 2 consecutive Fibonacci numbers, so you should get just about this number here. And so I just wanted to show you that because sometimes the proof by induction feels kind of magical, like you're not really getting any deeper insight into the sequence. Feels like you're just pushing symbols around. This is a great example where it's the complete opposite. The proof by induction actually gives us a deeper insight into the sequence that we might not have even found otherwise. So induction can even be really powerful in that way for gaining a deeper insight. Okay, so hopefully you enjoyed this lecture. I'll see you in the next one.